Good afternoon, everyone. So today we will be completing our problem on design of built-up compression members. So as uh, as we have proceeded with the problem in the previous three classes, we have got that there are two ISMC sections that will be used for the built-up compression member, which are the ISMC 350 channel sections. This is the gauge length, this is the width of the flange, okay, and this will be the height of the column. I have not like drawn the full height. It will be extended, and the total height will be along this, it will be 9 meter, okay, height, or you can say length of the column. Now in the last class I told you that the the thickness of the lacing will be 1 by 40 times the effective length of the lacing. So what is the effective length? Effective length will be how much? Isn't it? So for this you can see the notes in the previous steps. We have already calculated how this length can be calculated as 320 by sine 45, this one. Because this point is this one, this point is this one, this one is this, and this point is this one. So we wanted to find out what the length. So the length, suppose we have already got it as this one 320 we got, and for x what we did was we used trigonometry. Sine 45 degree is equal to perpendicular by hypotenuse, 320 by x, so x equal to 320 by sine 45. So this x is nothing but L, isn't it? This x is nothing but L. L is the length of the lacing. So 1 by 40 times of L. Okay. So how much we get from here? Please calculate. we get around 11 point something, isn't it? 11 point something, 11.13. So obviously we have to take a little more than that, so we will be taking 12. Okay, so we provide t equal to 12, because when we calculate it we get it around 11.1 or something like that. So we are providing thickness equal to 12. This thing is given in IS code. It's given in clause number, I'm telling you. See, it's given in clause number 7.6.3. Okay, thickness of lacing bars 7.6.3. All right, so now we have got the thickness. Now let us calculate the width. Okay, for width we again open our IS code. Okay, and you see the clause number 7.6.2. okay, for the width of the lacing. See what is written there. Three times of the diameter of the bolt. Okay, so we have not decided the diameter of the bolt. So let us assume one diameter. Let us take 16 mm dia bolt. So we have taken 16 mm dia bolt. So minimum width of the lacing should be 3 times of the diameter of the bolt. So it is 48. So we can provide 50. So we have provided width equal to 50. So we have got thickness equal to 12 and width equal to 50. Now what is our next step? It is to find out the FCD of the lacing. Okay, we have to find out the FCD. We have to find the FCD of the lacing. So for FCD, what we need to do? For FCD, you see lacing cross section. What? First draw the cross section. How will it look like for the lacing? So we can see here that the cross section of the lacing will look like this, because thickness is 12 and width is 50, isn't it? So we need to find out the FCD. You see, for a cross section which is rectangular, what is the buckling class? Buckling class is C. When the cross section is like this. Now, for FCD, first we have to know what is Fy. Okay, then if we can get the slenderness ratio, we can find out the FCD. Because slenderness ratio of the lacing, if we can get, then using the slenderness ratio and using Fy and using this buckling class C, we can use the page number 42 table to find out FCD. So let us find out the slenderness ratio. So for slenderness ratio, what is the formula? LE by R minimum. Effective length we already know. Okay, so both ends pinned means what? Isn't it? So LE we can directly write as L. Effective length is equal to the length. So now R minimum we get from what? I minimum, minimum radius of gyration we get from the minimum moment of inertia. So it has two moment of inertia along both axes. So first one is what? Moment of inertia about x-axis and moment of inertia about y-y. These x-axis and y-axis, don't confuse it with the y-axis, x-axis that are there for the channels, or the y-axis, x-axis for the built-up column as a whole. Don't confuse it. This is the exclusive x and y-axis for only the lacings. Only this x and y axis is drawn exclusively only for the lacings. It is not related with the x and y axis either for the channels or either for the built up column as a whole. So now let us find Ixx for the lacing. It will be how much? Ix will be what? B d cube by 12. B d cube by 12. Iy will be what? B d cube by 12. So which one is minimum here? Minimum is obviously this one. Okay, so the radius of gyration corresponding to Ixx will be the radius of gyration that we will be using here, because the radius of gyration that you will get for Iyy will be higher, because radius of gyration is proportional to the moment of inertia. So we will consider the radius of gyration about Ixx. So now radius of gyration, how can we find out? We know this I is equal to AR square. So area we know, I will be using this one. So corresponding R square we can find. From R square we can get R. So we'll do that. Area is which one? Area is this cross section area. It is what? 50 into 12 area. Isn't it? So you calculate it, how much you get. So r equal to root over 12. That is the radius of gyration that we get. Or we can write it as 3.464. So r minimum we have got. So now you find out the slenderness ratio. So you can calculate this value, how much it is. Okay, so this is the slenderness ratio we have got. Now we have to do one check. You see the clause number 7.6.6.3. It should be less than 145. So according to that clause, so we have already satisfied that condition. Now we have got the slenderness ratio, we have got the Fy value, buckling class we know. So you find out FCD. So you go to page number 42. Okay, so in page number 42 you can find out. So ultimately you will find FCD 75. Okay, approximately 75 you will get FCD. Now this is the what? This is the capacity of compressive stress that it can take. The lacing can take a compressive stress of 75 Newton per mm square. Okay, so the lacing can take a compressive stress of 75 Newton per mm square. So how much compressive load it can take? It will be what, 75 Newton per mm square into area, which is the cross-sectional area. So you calculate the value, how much do you get? 45 kilonewton. That means the lacing can take a compressive load of 45 kilonewton. Okay, now 45. Okay, we have got that 45 is the capacity of the lacing. Okay, lacing can take a compression of 45. So how much load is falling in the lacing actually? See, compressive load it can take is 45, means what? If this is the cross section, if you give a compressive load like this, then in that case it can take a load of up to 45 kilonewton. Okay, if you give a compressive load like this in this cross, so if you visualize it in this column, if this is the cross section, This one is the cross section. It can take a compressive load if it falls in this manner. Okay, just imagine this is a cross section. It can take a compressive load. The compressive load will fall like this, and in this manner it can take up to 45. That means if we give a load in this manner in the cross section, and if the load is below 45, then the lacing is okay. So similarly, just transfer your visualization here. This is the cross section. It should be a little like this. Okay, so if we give a load in this manner, in this cross section, so it if this load should be less than 40, this load on the lacing should be less than 45 kilonewton, because in this manner it can take only up to 45 kilonewton. So how will we check it? Okay, how will you check it? So there is for this you have to look into the IS code once again. You see the clause 7.6.6.1. Okay, what is it saying? It is saying that I'm just explaining you in my words. Okay, I'll not go into the reading of the clause. It's saying that the load that is falling on uh, the load that is falling on the column, okay, it is actually falling in this manner, isn't it? What was the load that we were talking about? The load was 1200 kilonewton, isn't it? So the 1200 kilonewton is falling like this in the column, okay, and it also has a transverse component. The load of 1200 kilonewton has a transverse component. First, it is falling vertically. This is the column length. Okay, it is standing like this. The load is falling vertically, but this load also has a transverse component, and that component is the transverse component of this 1200 load is 2.5%. Again, when you give a load of 1200, now there are two channel sections. Okay, so each channel section will take half of it. Okay, they will divide the load into two. Okay, so I'm just drawing it. You just watch and try to understand. The load is a total of 1200, so there are two channel sections, so each will take half of it. Okay, it will take care of the 600, and this channel section will take care of the 600. Okay, so each panel will not take 1200 directly. 1200 is the total load, and it is divided in among the two channel sections. So this is 600, this is 600, so we can write it directly as 600. So this 600, according to clause 7.6.6.1, will have a transverse component which is 2.5% of 600. Okay, this 600 will have a transverse component which is 2.5% of 600. How much is this fellow? Find out. 15 kilonewton. Okay, now this is going in this manner. So what will be the load that will be falling? This load will have a component like this, which is falling on the lacing cross section. So how much load of this value, that is, this is 2.5 of 600, that means it is 15. I'll write it 15 here. So this 15 will have a component like this. We have done this resolution of forces in our first year and all. So if this is 45, this one is also 45, obviously. So we want, this is the applied load, okay? 600 is the applied load and 15 is also the applied load. So we have to see the component of 15 that is going like this. And that component should be less than 45 kilonewton, because the lacing has a capacity of taking 45 kilonewton like this. And if we resolve it and we see that the component of the applied load is less than 45, then it is safe. So 15 is the applied load. The component of 15 in this direction will be how much? We can just use trigonometry. So we can, if we take it as x, so cos 45 is equal to base by hypotenuse. So x becomes, that means the load in this direction becomes 15 by cos 45, which is equal to 21.21, and 21.21. So that is a sort of checking that we have done. So 21.21 is the load applied in this direction, and the capacity of the lacing to take a load in this direction is 45. So obviously the capacity is more than the applied load. So ultimately the lacing is safe. So we are almost 90% through the problem. Okay, just a little bit of step is remaining. I don't have much time today, so I will not be able to continue it further. You see, we have checked the lacing and compression lacing is safe, and then we will also be checking the lacing in tension. You see, if the load, that is the only step that is remaining. You see, if the load is 600, okay, here and 600 here, okay, suppose the load will reverse its direction, we have to take into account the reversal of direction of load. So if 600 goes in opposite direction, then what will happen? This load will go in this direction, this load will go in this direction, okay, all the direction will change, every direction will change. So if this load changes its direction like this, in this way, and this load changes its direction in this way, okay, and everything changes in direction, then this compression load becomes tension. So we also have to check whether the lacing can take a tension and of how much, okay. So that is a very small step, but still I don't have much time to do even that step. I will complete it in the next class tomorrow, and then tomorrow we will be discussing design of cassette base, okay, sorry, design of base plate. So see you tomorrow. Thank you very much.